So, we all hear about how quantum computing is going to change the world, right? But there's this huge catch. Building one that's actually powerful enough to matter requires a complete revolution in engineering. Today, we're going to dive into a major breakthrough that might just be that revolution. And it uses a pretty surprising tool to control the quantum world: sound.
The biggest hurdle for quantum computing isn't just about cranking out more quantum bits or qubits. The real headache is scale. I mean, to do anything really useful, you have to precisely control millions of them, all at the exact same time. It's a staggering engineering problem that honestly has seemed almost impossible. Until now. And this quote from Professor Matt Eichenfield just nails it. It perfectly captures how absurd the old way of doing things is. The tools we currently use to control qubits with lasers are these big, clunky, power-hungry boxes. Scaling that up would literally mean building a warehouse full of them for just one computer. It's insanely expensive, it pumps out a ton of heat, and it's just completely unsustainable. Okay, so if building bigger and bigger is a dead end, what do you do? Well, you've got to build smarter and way smaller. That's exactly what researchers at the University of Colorado Boulder and Sandia National Labs have done. They've developed a revolutionary new device that completely sidesteps the scaling problem by putting the entire solution on a tiny little microchip. And check this out. This slide is just fascinating because it shows you this incredible contrast. On the left, you've got the whole chip sitting right next to a dime, mean it's tiny. But then, boom, on the right, we zoom way in to a microscopic cross-section, and you see this mind-bogglingly complex, layered structure. This isn't just some simple little part. It's a whole nano-engineered system built for one thing: the precise control of light. So what makes this little chip such a game changer? Well, it really comes down to three key things. First, it can handle the intense laser power you need for quantum control without breaking a sweat. Second, it's just ridiculously efficient at manipulating that light. And third, and this might be the most important part, it can be mass-produced using the exact same tech we already use to make all our computer chips. Okay, but how in the world does it actually work? This is where the physics gets super clever, almost like something out of sci-fi. At its heart, this device uses a wild principle. It uses high-frequency sound waves to grab hold of a beam of light and control it. Right, the fancy term for it is an acousto-optic modulator. Let's break that down. Acousto for sound, optic for light. That's really it. You zap it with an electrical signal, it creates a tiny vibration, basically a sound wave pitched so incredibly high it's just pure physical energy, and that vibration gives you perfect control over a laser beam passing through the chip. And here's how it all comes together in 4 simple steps. First, you hit it with a microwave signal. That signal makes a special material, a piezoelectric layer, vibrate billions of times a second. Those vibrations, these powerful little sound waves, travel through the chip and literally squeeze the tiny channel the laser light is traveling through. And that physical squeeze is what changes the light's properties, giving us the exact, precise control we need to talk to a single qubit. So the how is brilliant, for sure, but it's the performance that really makes this a revolution. Let's look at just how much better this new on-chip approach is compared to those old bulky devices. Seriously, the numbers are just staggering. First off, get this. It needs 15 times less voltage to run. That's a massive deal. A huge drop in just the raw electrical power you need to get this thing going. And that's just the start of the massive power savings. And that leads right to this. This is really the headline number. The chip uses 100 times less microwave power to do the exact same job. 100 times. I mean, that is an absolutely transformative improvement. And remember, less power doesn't just save on the electric bill. It means way less heat, and heat is the absolute arch nemesis of a working quantum computer. And this chart just lays it all out, plain as day. Look at that huge bar on the left. That's the insane amount of power the old modulators guzzle down. And then look at the tiny little sliver on the right. That's the new chip. It's not just a little better, it's in a completely different league. This is the kind of paradigm shift that makes scaling to millions of qubits suddenly seem actually possible. Okay, so you have this amazing prototype. But a great prototype isn't enough, right? To build a real quantum computer, you need millions of these things, and they all have to be perfect. And that's where this tech has one more ace up its sleeve: how it's made. See, the chip is made using something called CMOS fabrication. Now, that might sound technical, but you're probably holding it in your hand right now. It is the exact same industrial process used to make billions of microchips for your smartphone, for your computer. It's the most scalable manufacturing technology humanity has ever invented. And that means we can make millions, even billions of these quantum-controlled devices cheaply and reliably. And this quote from researcher Niels Otterstrom just frames it perfectly. He compares it to the jump from old-school vacuum tubes, those giant, hot, clunky glass things, to the tiny little transistor. And we all know what the transistor did, right? It didn't just make computers there, it made our entire modern digital world possible. This is that kind of leap for quantum computing.
So this right here, this is the end game. This is the ultimate vision. All those little boxes and lines you see, those are all the other bits and pieces you need on a chip. Splitters, filters, the whole shebang. The goal is to cram all of that, plus our new modulator, onto one single, fully integrated all-in-one control chip. One chip to rule them all.
And that's why this quote from researcher Jake Freedman hits so hard. He says this device feels like one of the final pieces of the puzzle just clicking into place. For anyone who's followed this field, you know that this control problem has been this giant shadow hanging over everything. And now, it looks like we might finally have a real, workable solution. Which brings us to the big final question, doesn't it? This tiny little chip, this amazing dance of sound and light, it isn't the end goal itself. It's the key. It's the thing that might finally unlock the door to huge, powerful quantum computers. So the real question isn't about the chip. It's about what's on the other side of that door. What new medicines, new materials, and new discoveries are waiting for us when we can finally compute at the quantum level.